represent continuous LAM beyond lifelong simultaneous localization and mapping through continual learning. Deploying a SLAM system to the open world poses great challenges, requiring the system to be robust to weather and lighting conditions, drastically different environmental structures, as well as different camera sensor characteristics. Lifelong SLAM partially addresses these challenges by considering the long-term operation of a robot in a dynamically changing environment, but is limited to a single bounded area of deployment. Recent works attempt to relax this assumption by leveraging domain adaptation techniques, including both regularization and online adaptation of the internal state of the employed model. The task of continuous LAM takes the next step by requiring an algorithm to quickly adapt to unseen environments while effectively memorizing knowledge from previously seen environments to minimize adaptation when revisiting them. To evaluate the performance of continuous LAM systems, we propose two novel metrics, namely adaptation quality AQ and retention quality RQ. The adaptation quality metric measures the ability of a method to effectively adapt to a new environment based on experiences from previously seen environments. The retention quality metric captures the ability of an algorithm to preserve long-term knowledge when being redeployed to a previously encountered environment. To address the continuous LAM task, we propose CL-SLAM, a dual network architecture that consists of an expert and a generalizer. Both networks share the same architecture and are trained in a self-supervised fashion. The dual network is based on a self-supervised method for monocular depth prediction, DepthNet, and a visual odometry estimation, PostNet, although the general approach is not limited to a specific architecture. The expert network aims to produce the best possible online odometry estimates for the current data. Therefore, its internal model state is only updated based on online data. The Generalizer Network, on the other hand, focuses on the long-term learning across environment. Its internal state is updated based on combined data from the online stream and a replay buffer containing previously seen environments. We compare our proposed CL-SLAM with three baselines that are inspired by previous continual learning works. First, B-Fixed utilizes network weights that are fixed after the pre-training stage, without any online adaptation. Second, B-Expert uses a single set of network weights, which are continuously updated based on the current data. This corresponds to only using the expert network in our architecture, without resetting the weights after every deployment. Finally, B-General leverages a replay buffer built from previously seen environments. This method corresponds to only using the Generalizer Network in our architecture, without a specialized expert network. In this experiment, we evaluate CL-SLAM and the baseline methods on the sequence 9 of the KITTI dataset, after pre-training on the Cityscapes dataset. Note that in the initial adaptation step, our method is the same as B-Expert, as both strategies are initialized with the network parameters from pre-training and only updated based on the current online data. Conversely, B-General also records the experiments from Cityscapes using a replay buffer. The advantage of this approach becomes visible in the subsequent experiment. Here, we evaluate CL-SLAM and the baseline methods on the sequence 10 of the KITTI dataset, after pre-training on Cityscapes and deployments on sequence 9 of the KITTI dataset and the Oxford robot car dataset. Although B-Expert is able to reproduce the general shape of the trajectory, it requires warm-up time, causing a large drift in the initial frames. On the other hand, B-General can leverage experiments from previous deployment on KITTI data. Based on these insights, our proposed CL-SLAM combines the advantages of both strategies, achieving the best performance among all the considered methods. For more details and the code of our proposed method, we refer to our paper and the project page.